Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on September 17th, 2025, just yesterday. The standout result is a method that reliably uses external tools to boost mathematical and code reasoning, reaching state-of-the-art among similar-sized models, and doing so with fewer tokens at inference. The paper is titled THOR, Tool Integrated Hierarchical Optimization via RL for Mathematical Reasoning. And as we will see later, the implications for model training are quite significant. In short, this paper pairs an actor-critic data generator, a two-level reinforcement learning scheme, and an execution-guided self-correction loop to turn tool feedback into better final answers. Also, the authors shared the official GitHub repo. You'll find the THOR codebase with assets, inference, and training folders, an Apache 2.0 license, and a detailed README outlining TIRGen, hierarchical RL, and self-correction. Setup and usage sections are marked TODO, but the implementation and paper details are clearly organized. Alright, Figure 1 distills the whole story. The method builds better tool-integrated reasoning data, trains with two-level reinforcement learning, and then self-corrects during inference, which together drives strong benchmark gains. The left side flags problems with current datasets, while the center shows an actor and critic turning problems into executable tool calls that feed hierarchical training. The right side summarizes accuracy improvements on AIME and AMC because successful code execution guides both learning and correction. So, Figure 2 shows how the team constructs tool-integrated reasoning data that matches the model's own style. The pipeline runs an actor that writes a short reasoning step, while a critic checks if part of that step is code solvable, which means a calculator like Python can execute it precisely. The critic extracts the logic, converts the calculable part to Python, executes it, and feeds back the results so the actor continues. A multi-stage filter then enforces format, code quality, and difficulty balance to yield the cold start dataset. Alright, Figure 3 presents the core training loop that ties tool use to better answers. The top panel shows trajectory level reinforcement learning, which rewards a full reasoning path only when the final answer is correct, so the policy learns problem-solving strategies. The middle panel adds step-level optimization, meaning failed code calls are split at a prefix, and the model regenerates just the faulty suffix. The bottom panel illustrates self-correction at inference, where execution feedback triggers targeted retries until a tool call succeeds. So Table 1 compares accuracy across math benchmarks and shows that the proposed approach consistently ranks at or near the top for both smaller and standard scale models. The table groups models by whether they are reasoning or non-reasoning, which clarifies that tool use lifts both categories. The green highlighted rows mark the method's variance, and their average scores lead each block with strong gains on AIME and AMC. These results matter because they pair high accuracy with low token usage. Wrapping up, two takeaways stand out. Tool-integrated data plus two-level reinforcement learning makes execution success a reliable guide to final correctness, and targeted self-correction turns failures into quick recoveries, saving tokens while boosting accuracy. The broader implication is clear. Smart tool use can lift both reasoning and non-reasoning models. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.